Hello, my name is Aaron Bartholomew, a computer science student at the University of Wisconsin-Madison. In this video I'll provide an overview and brief analysis of my final project for Computer Science 777, Computer Animation. The project is called Sprite Animation from Motion Capture, Computer Vision, and Clustering. Sprite animations are often used in two-dimensional applications in order to convey highly stylized motions. These animations are employed using sprite sheets, or a grid of character poses which are drawn in sequence according to the motion. In order to create a quality sprite sheet such as this one from Braid, an artist must painstakingly draw the character from every cell of the sprite sheet. This can be a very tedious process. The artist must maintain consistency and timing of the motion at every frame, which can be absurdly challenging. If the application uses more than one potential viewing angle, such as a top-down view as well as a side view, the artist must draw the same motion from multiple perspectives while maintaining its consistency. The solution to this consistency problem is to use pre-rendered sprites, or to render a three-dimensional model performing the motion from the desired perspective multiple times, and using the renders as grid cells. Here is an example of a pre-rendered sprite. Although this maintains consistency of the motion, the aesthetics of the sprite are limited to three-dimensional rendering techniques, which is not always desirable considering that sprites tend to use highly stylized, non-photorealistic visuals. Also, without supervision, this method can return a lot of redundant frames, providing a sprite sheet that simply has too many frames to be feasibly stylized by an artist. My system provides a technique that attempts to create a minimum frame sprite sheet using motion capture data. The result is intended to both maintain quality and consistency of the original motion, as well as be feasible for artist customization. First off, I'll discuss the interface. Using the G3D engine as a foundation, this interface allows the user to load ASF, AMC, or BVH format motion capture files. These motions are represented by a simple skeleton. You can freely play back these motions. The user can preview the sprite animation in a window in the lower left corner of the screen. They can adjust the zoom and choose from 3 different viewing angles. Once the user is satisfied with the preview, they can set some parameters for the sprite sheet rendering process. Grid dimensions is the size in pixels of each individual cell. Distance threshold defines how the system will evaluate redundancy of 2 images. The higher the threshold, the more different 2 images can be and still be considered redundant. Finally, the user can specify how many frames of the motion they want to render. By default, this is set to every frame of the motion. If the frames are too high, this can be time-consuming to process. Setting a lower frame number will cause the system to render at uniform intervals. Here's what the sprite sheet looks like without any processing. There are 100 frames in this sheet. Here's what the sprite sheet looks like after eliminating redundancies with a distance threshold of 10. This has 44 frames. Here's the resulting sprite animation. As you can see, it maintains the semantics and quality of the original motion. In order to eliminate these redundancies, the computer needs to be able to determine when 2 images are similar. Using Christina De Juan and Bobby Bodenheimer's paper, Cartoon Textures as inspiration, I implemented a Hausdorff distance metric, which evaluates the similarity of 2 images from the per pixel distance to the nearest edge of one image that are on the edge pixels of another. This is accomplished by comparing the image's edge maps and distance maps. An image's edge map is found by using a canny edge detector, which uses 4 filters to find the vertical, horizontal, and diagonal edges of an image. Here's an example of an edge map from a single frame. Once an edge map is acquired, a distance map is computed using a fast approximate Euclidean distance transform known as Danielson's algorithm. This algorithm uses the edge distance of neighbors across 4 raster scans to approximate the distance from a pixel to its nearest edge. Once all edge maps and distance maps have been computed, all of the images are compared and their distances are stored in an upper triangular matrix. The algorithm now begins clustering the images. Since we don't know ahead of time how many clusters there will be, we cannot compute a mean or median image that maintains motion semantics. I use hierarchical clustering to find redundancies. Here is a visualization of the cluster hierarchy. The system uses agglomerative hierarchical clustering, where each image starts as a disjoint cluster and is then recursively merged greedily with the most similar image found in the distance matrix. When 2 clusters are merged, a new cluster is created where the parent nodes of the two merged clusters become the left and right children of the new node. This forms a binary tree where the leaf nodes with greatest height are the most redundant frames in the animation. You can clearly see how this is the case in the lower right portion of the hierarchy. Once the hierarchy is in place, the nodes are pushed into a priority queue using node height as a key. When popped, the algorithm traverses up the tree until it reaches a node where the current image has a Hausdorff distance that is greater than the user-defined distance metric. At this point, the subtree is cut from the hierarchy, and every frame of the subtree is replaced with the image in the original pop node. Once all redundant frames are replaced, the sprite grid motion is remapped so that the base redundant image will be used instead of the original redundant image. Implicitly, this method suggests the use of sprite motion graphs. The system can load multiple motions, render them to the same sprite sheet, and then make connections between their redundant frames, so that when the frame sequence reaches a redundant frame, it can choose to continue the motion at different cells in the sprite grid. Here are the connections made between the running and walking motions you saw earlier. The white lines represent where the connected frames can be played immediately after the other, and theoretically maintain consistent motion since the frame before it was redundant. Unfortunately, the result isn't that good. The character ends up popping between the different motions. This is the case because the method does not take into account the similarities of the surrounding frames of the redundant image, so there isn't any sort of transition from one motion to the next. One interesting result is that my program is surprisingly good at maintaining the semantics of a motion. Here's a running motion after it has been reduced to only 3 frames from a very high distance threshold. Keep in mind the sprite resolution is very poor. Although the animation is extremely choppy, it still conveys a running motion. This indicates the quality of the Hausdorff distance metric is extremely sensitive to slice changes in similar images, so even when the distance threshold is really high, it's pretty much guaranteed to retain the perceptually important poses that define a motion. Another interesting result of the application is the remapping of the motion sequence. Here's the same sprite that uses different sequence mappings. The motion on the left replaces redundant frames with a single base frame. In this case, the first 8 frames of the motion are replaced with one frame, thus resulting in the appearance of a lag. Although the sprite maintains the timing of the original motion, it does not look visually appealing. The sprite on the right simply eliminates the redundant frames. Although the timing is off, the animation appears far more continuous, which is most likely due to gaps in the motion being too small to be perceivable. Finally, here's an example of the intended purpose of this program, which is to customize minimum frame sprite sheets. Here, this sprite has been customized to look like a man burning alive. Clearly, to have any use, this program needs to be further extended to allow for the character skinning. Alright, thanks for watching my video. Please give me an A.